Hello, everyone. Today we will talk about fundamental bioinorganic chemistry. Many of the themes that we will discuss today and over the next series of lectures come from the first two chapters of the Bioinorganic textbook. And the idea is that we're going to build our fundamental understanding about metal properties that will help us to appreciate the roles that metals play with respect to human health. All right, let me go ahead and project. All right, so fundamental bioinorganic chemistry. Well, at the root of this field is coordination chemistry. So let us start there by defining what exactly is coordination chemistry. As I mentioned in our previous course, metals have always played a very important role in chemistry, in particular, due to their medical application. But formally, the branch of chemistry that has to do with compounds made with metals was founded by Alfred Werner in the late 19th century. This particular field focuses on the properties and structures of coordination compounds. What exactly are these compounds? Well, they're composed of the bonding interaction between metal atoms or ions, typically transition metals, and one or more ligands. As we will discuss in a moment, ligands are those species that can form a bonding interaction with metals. When Alfred Werner introduced this field, he really expanded the concept of what constitutes a bonding interaction, but also very importantly, the type of structures that can be chemically formed. At its core, the premise of coordination compounds involves an interaction between a metal and a ligand in which an electron pair from the ligand is attracted to the metal. So we're essentially looking at a nucleophile-electrophile type of interaction. So the electron pair from a ligand interacts with a metal species and it forms a metal-ligand bond. This type of interaction is a Lewis acid and base adduct formation, and it underlines metal-ligand bonds. Now let us review Lewis acid and base theory. Well, in this theory, the identity of an acid is a species that has the capacity to accept electron pairs, and a base is a species that will donate electron pairs. Looking at it from the context of a coordination compound, then, metals are Lewis acids and ligands are the Lewis bases. The ligands are atoms, ions, or molecules that donate electron to a metal center. All right, so let's add that here. They are our Lewis bases. So here we see a representation of a metal ligand adduct. We're looking at silver 1 plus interacting with two equivalents of an ammonia ligand, which is referred to as an amine. What we obtain is this silver ammonia adduct that consists of the stoichiometry of one metal with two ligands, and it actually forms a linear structure. The type of bonding interaction between that metal center and the two nitrogens is of a dative bond. Now, when we think about bonds, we normally think about the recipients each contributing an electron that will be shared. But in this context, the electron pair is coming exclusively from the Lewis base. Now, I will say that this is an oversimplification about metal-ligand interactions because there are examples where the metal can actually contribute electron pairs. But at its core, fundamentally, when we look at metal-ligand interactions, we're really focusing on that initial contact coming from the electron pairs of the Lewis space. Now, defining the properties of this bond, it is of a coordinate covalent form. It features both covalent and ionic properties. So let's discuss some key ligand properties. Well, ligands can be neutral or charged. And here I present a table of some of the common ligands, neutral ligands, with their common names. So these would not be the IOPAC names for these particular species. So we have the representation of the amines and also other ligands that are commonly seen in the literature. Here I present a table for ligands that adopt an anionic charge. So we have some of the key common ligands, the halides, the pseudohalides, and others. Now, it is quite common that when a ligand is charged, that it would be anionic, and that is because of the electrostatic attraction between metals, which are seeking electrons, and that negative charge from the anions. Now, that is not to say that ligands cannot be cationic. So there are examples present in the literature. Here are a few of them. The hydrazinium ligand as one, or the nitrosyl ligand as another. But it is less likely or less favorable for a ligand to be cationic due to the potential electrostatic repulsion that can exist between the ligand and the metal. On one level, to do with the charge interaction, and also, as we will discuss later on, potential repulsions that can occur between the metal centers electrons with these type of ligands. Another really key characteristic of ligands is their denticity. As the root of this name implies, dent, referring to dental, okay, it talks about how many contacts at which a ligand can bite onto a metal, if you want to think about it like that, to grab onto a metal, form a bonding interaction. So this property defines the number of atoms at which a ligand can bind a metal. So let's consider the aqua ligand. The aqua ligand is the water molecule. Now, water often plays solvents when we're talking about coordination chemistry within a biological context, but it very much is a ligand. Now here we're looking at the typical structure that we're all familiar with, this bent structure of the water molecule. And so we're looking at the central atom oxygen and its free pair of electrons. It is these pair of electrons that can be a source of bonding interactions with metals. So considering the interaction of one aqua ligand with a metal, we can form this adduct where you have one contact between the metal and the aqua ligand through the oxygen atom. Now you may ask yourself, well, how do I know that that is a likely interaction? Well, coordination typically occurs at the most electronegative atom. We use prefixes to distinguish the denticity of ligands. The coordination demonstrated here is monodentate. Here we're using the prefix mono to imply that one contact, due to the metal atom at one atom or site. So here I present a table that distinguishes the denticity of ligands. So we have the list of prefixes and the number of coordinating atoms coming from a given ligand. Mono implies one coordinating atom, bi implies two, tri implies three, tetra implies four, and so forth. Now let's structurally explore denticity. So here I present to you a generic compound where the metal has a coordination number 6. Okay, what that means is that there are 6 atoms coordinated to that metal. And a coordination number 6 has a typical geometry, and we'll talk about that in a moment, this idea of a correlation between coordination number and geometry. But I want to use this example, or this particular metal compound, to establish ligand denticity. So if we have a ligand, A, that has only one contact with a metal, well, that, as we know, is monodentate. We're just going to mentally ignore the X's because they just represent a position being held around the metal center. If we have a ligand that has 2 points of contact, then it's bidentate. Okay, so this is to say that there are 2 atoms within a general ligand that will come in contact with the metal. It does not mean that there is a bridge or a direct bonding interaction between those 2 points of contact. Right? I'm just using a visual to help us to understand the idea of what bidenticity means. So here we have a tridentate ligand, a tetradentate ligand, a pentadentate ligand, and a hexadentate ligand. A very important descriptor is for a ligand that can bind at 2 or more sites. Such a ligand is referred to as polydentate, or more commonly as a chelator. You probably have heard of chelation therapy as something that is used to treat the overdose of a particular element within the body. A related descriptor of ligands is hapticity. The coordination of a ligand to a metal center via an uninterrupted and contiguous series of atoms. Hapticity is described with the symbol eta. So let us focus on a particular molecule that can serve as a ligand, which can alter its coordination modality in terms of hapticity. So here we're going to focus on metal complexes with the cyclopentadienyl anion. All right, so here's our abbreviation C5H5, negative charge. It is anionic. So let's talk a little bit about this ligand as an anion in terms of its capacity to interact with the metal center. So here we actually have 3 electron pairs that will be involved in metal binding. They are the free electron pair and the 2 double bonded pairs. We're going to see how this particular ligand can interact with the metal in different ways. So here I present to you a visual of 3 possible interactions. To the left, we have what we would normally perceive as something of a monodentate coordination. Now, in terms of hapticity, we're looking at a 1-point contact, so 1 atom, and so we refer to this as eta 1. And we're interacting with the free pair of electrons. But if instead we have 2 electron pairs interacting with the metal, and through that interaction, the metal comes into contact with 3 of the carbon atoms, well, what we have here is an eta 3 hapticity. And so I've used these stars to represent the carbons that will interact with that metal through those electron pairs. And then finally, when we have the metal interacting with the entire ring via the 3 electron pairs, well, then here we have an eta 5 hapticity, where now all 5 carbons of the ring have a contact with the metal through those 3 electron pairs. And now you have this as this aromatic character within the ligand. Note, hapticity and denticity do not necessarily go hand in hand. And I will emphasize this by using the eta 5 hapticity as a point of reference. Eta 5 may be considered by some coordination number 5 because of the 5 carbon ring, so those 5 carbons are in contact with the metal center. But there are those that would refer to that as coordination number 3, because technically that metal is interacting with 3 electron pairs. But it can be more complicated than this. How do we classify the coordination number of a compound such as titanosyne dichloride? Well, structurally, when we look at this compound, what do we see? We see 2 cyclopentadienyl rings, so they're typically abbreviated as CP rings. So we have 2 of them. We have 2 chloroanionic ligands interacting with that metal center. The titanium is titanium with an oxidation state of 4. And in terms of structure, well, the geometry that we have here is tetrahedral. I alluded to previously that there is a correlation between geometry and a coordination number. So that actually complicates the perception of what is the coordination number, because now if we think about what I was mentioning previously about the eta 5 interacts with the metal center, well, one can think of this structure as being potentially coordination 8 if each CP ring has 3 electron pairs interacting with the metal, or even a coordination number 12 where perhaps if you consider each CP ring as a source of 5 carbons interacting with the metal. But then focusing on that tetrahedral geometry, well, that would suggest a coordination number 4. All right, and we're going to look at that in a moment. So it's not entirely clear, and I'm not sure that the field actually would have a set definition here. But let's explore this concept stemming from inorganic chemistry, the fundamental undergraduate course, this idea that a coordination number will have a given geometry. And that is because the field of coordination compounds adopt highly organized structures, and depending on the nature of the ligand, we have predictable geometry. So let's look at coordination number as dictated or as dictating an idealized geometry. So here I'm going to give you a list: coordination number, CN, the abbreviation, geometry, and structure. When we're talking about coordination number 1, really this descriptor of a geometry is trivial. We basically have this one point of contact between the metal and the ligand. But then when we're to start with coordination number 2 or more, then geometry actually is a significant thing, a real thing. In coordination chemistry, when we're talking about transition metals, coordination number 2 defines this type of structure where you essentially have now a defined geometry or a defined bond angle. Here, the ligand-metal ligand bond angle is 180 degrees. Coordination number 3 will have an ideal trigonal geometry. And so here now, we have these 3 ligands around the metal center and a set ligand-metal ligand bond angle of 120 degrees. When we reach coordination number 4, we actually have 2 possible geometries. One of them is tetrahedral, and you should be quite familiar with this, especially having taken organic chemistry, and when you talked about a carbon center and having a coordination number 4 for substituents around it, adopts a tetrahedral geometry. So here we have the ideal structure for a tetrahedral geometry. We have our metal center and 4 ligands interacting with it. Remember, this is the structure that we saw for the titanosyne dichloride. Well, here, our ligand-metal ligand bond angles are 109.5 degrees all around this structure, right? The other possible geometry is square planar. And so here now, we have a different ligand-metal ligand bond angle where you have these right angles, 90 degrees, and you also have a ligand-metal ligand bond angle of 180 degrees. Now, at this moment, it wouldn't be clear what conditions will dictate a tetrahedral geometry or what conditions will dictate a square planar geometry. That's something we'll discuss later. Coordination number 5 also has two different types of geometries. One of them is trigonal bipyramidal. And so here now, it becomes extremely important distinguishing where the contact between the ligand and the metal occurs. Structurally, we actually have two distinct positions around that metal center. We have what is the axial position. So you have two ligands that are located on an axial position. They're actually 180 degrees apart from one another. But then you have a set of ligands that are on an equatorial plane. All right. So it's very important that you recognize how I'm drawing these structures. So you're familiar with the tetrahedral geometry, but now it can become complicated to see in a three-dimensional manner something that is drawn two-dimensionally. So I do use these wedges to give us a perspective. When I use these straight lines, I'm just going to highlight the ones that are the straight lines. Okay, so I've just highlighted those three. My implication is that that is on the plane of your screen. But when I use these wedges, I'm going to resize them again. These wedges are to imply that they're not on the plane of your screen. The ones that are dashed are going to the back of your screen, and the ones that are in bold coming towards you. So the idea is to see that you have these three ligands on a plane that's actually perpendicular to the plane of your screen, but also perpendicular to the axial position, right? So they form this trigonal type structure. That trigonal is the source of the trigonal component of the name. All right, so now given this information, I actually want to clean this up a bit. So clearing that up. So you have that trigonal equatorial plane, and if you draw the points of contact between each of the ligands and the equatorial plane and the ligands in the axial position, what you would get is the trigonal bipyramidal structure. So you get that may not be so clear to see, but that is in essence what the trigonal bipyramidal name comes from. All right. So once again, let's clear this up, and now let's focus on the ligand-metal-ligand bond angles. Now, when we're looking at the ligand from the axial position with respect to a ligand in the equatorial plane, we form these 90-degree right angles. When we're focusing on ligands within the equatorial plane, so ligand-metal-ligand bond angle, we have 120 degrees. Okay, so there are two different ligand-metal-ligand bond angles, and obviously you also have the third one that has to do with the arrangement of the ligands in the axial position, 180 degrees from one another. Now this is to contrast with the geometry of square pyramidal. So here you have a structure like this where you also have two distinct positionings around the metal center. You have the one ligand in an axial position, and you have four ligands in an equatorial plane. They actually form the square, okay? And if you were to draw the points of contact between the ligands in the equatorial plane with the ligand in the axial position, you will see how you get this structure that is square pyramidal. All right, let's clean that up. Now let's talk about the ligand-metal-ligand bond angles, and this is what makes this geometry distinct from the trigonal bipyramidal, where when we're looking at the ligand in the axial position with respect to a ligand in the equatorial plane, you form these 90-degree bond angles, and then ligands within the equatorial plane here, you have a ligand-metal-ligand bond angle of 90 degrees. Also within the equatorial plane, you have another angle of those ligands that are across from one another. So that's ligand-metal-ligand bond angle of 180 degrees. All right, so it may not be so clear when you would have a trigonal bipyramidal structure, when you have a square pyramidal. That's something we will also discuss throughout the course. Now, the last coordination I want to talk about is coordination number 6. And this is commonly an octahedral geometry. So I already referred to one example of an octahedral structure. Now let's look at the details. Here too, we have 2 distinct positions. This structure is more in line with the square pyramidal structure. All right, so here we have the axial positions. We have the ligands that form this square plane. And if you were to draw the points of contact, it's not so easy to see, but you see how you get this octahedron, which is the source of the octahedral name. All right, so let's clean that up for visual clarity. Let's talk about the ligand-metal ligand bond angles. So with respect to a ligand in the axial position versus next to a ligand in the equatorial plane, we have 90 degrees. If we're looking at ligands that are next to each other in the equatorial plane, you get a ligand-metal ligand bond angle of 90 degrees. You also have the arrangement of the ligands that are across one another on the axial position. That gives you 180 degrees. And then you also have the ligands that are across from each other within the equatorial plane that also gives you 180 degrees. I will note that formally we have 2 positions, the axial and the equatorial plane. But if you were to take this structure, okay, and you were to move it all around different angles, you will see that in an ideal octahedral structure where all the L's are in the same atom, the U would have all of the positions being equivalent. But no octahedral compound, no coordination number 6 compound will be ideal. All right. So now that we have appreciation of how coordination number can help to dictate geometry or give us an understanding of structure, let's talk about what is the underlying factor or factors for the metal ligand binding preference. And here we're going to zoom in on the hard soft acid base theory, abbreviated as HSAB. It underlines that preference for metal ligand interactions. This theory expands on the Lewis acid and base theory. Remember, the Lewis acid being something that can accept electron pairs, the Lewis base being something that can donate electron pairs. Well, Pearson and Chat recognized that the polarizability of species was correlated with the preference of species to interact with others. All right, so here the key term is polarizability. So just imagine an electron cloud. Now this electron cloud is localized at a particular atom, is not going to be very polarizable. But if that electron cloud is bigger and is able to move around, you can have a potentially a dipole form, even if it's instantaneous. This is kind of the idea that you need to think about. The delocalization or lack of delocalization of electrons within species or even at a particular atom that will interact with a metal center or the particular atoms within a metal center. Okay, so because we're talking about both the Lewis acid and the Lewis base. All right, so to establish this theory, we're going to consider a random base interacting with a non-polarizable and polarizable Lewis acid. So here we set up this analysis. So our random base is B with a pair of electrons, and a proton is the non-polarizable Lewis acid. A methylmercury is the polarizable Lewis acid. All right, so we're focusing on the strength of the interaction. All right, so this equilibrium and the strength defined by the values of K, that affinity constant or formation constant, however you want to refer to it. Affinity is why this is actually called an affinity scale or scales, because we're doing this analysis to compare the relative affinity that these random bases will have. So we're going to form these adducts, the proton adduct, the base, and the methylmercury adduct with the base. Well, it turns out that the strength of interaction is what was used to distinguish the type of properties of the base. So in this context then, if the affinity was much, much higher for the proton, remember that is our non-polarizable Lewis acid, okay, then the base was defined as hard, meaning that it was non-polarizable and had a high charge to size ratio. Now, if the affinity for the proton was much, much less than the affinity for the methylmercury, well then the base was defined as soft. That's the opposite then of what defines hard. It's polarizable and has a low charge to size ratio. But now if the affinity is comparable, well then that defines a base that is intermediate or borderline. These same definitions apply to metals in terms of whether the metal is non-polarizable, polarizable, or in between. Okay, so it's not just a description for the base. Now you may wonder, how can you readily identify something as being hard and soft? And then obviously acid and base. Well, the acid and base one, at this point, I would suspect that many of you know how to be able to do so. It stems from the periodic table trends properties that we've all talked about over the years. But let's review one really key periodic trend, which has to do with the size of elements. All right, so here you have the IUPAC periodic table, and we'll just remind everyone, as you go down the rows of the periodic table, what you will see is that the elemental size increases. Why is that? Well, that's because you have more and more orbitals, right? And so now you're going to have more distance between the outer electrons from the nucleus, right, the positively charged nucleus. And so you are basically expanding these electron clouds. So these atoms are bigger as you move down the periodic table. As you go from left to right, the general trend, and I emphasize general because it's not 100% correct, is that the element size, the atom size will decrease. Okay, and that in part has to do with that in addition to adding more electrons, you also have more protons, and there's going to be a great electrostatic attraction between the electrons and the protons, and that's going to result in the atoms becoming more compact. All right, so this is really important in terms of our descriptor of a species that is hard and soft, okay? Because it depends on the charge to size ratio. So the general understanding that actually, this should be the opposite. So I've actually corrected this in your slides that I've sent to you guys. The smaller the size, and also the bigger the charge, the higher the charge, the harder the species will be. And so something that also helps us to readily identify something that's hard or soft is the electronegativity of the elements. Okay, remember, this is a property specific to an atom. It's not a property of the whole molecule. We're talking about a molecule that can interact with a metal. All right, so the electronegativity of the elements helps us to appreciate, the sense of how polarizable or not polarized something is. All right, so remember that the electronegativity refers to how strongly an atom holds on to its own electrons. So the higher that number is, the greater the electron localization will be, and thus the higher the hardness of that species will be. All right, another thing to remind ourselves are generally where in the periodic table you would expect to see things that would be acidic and basic, right? So keep in mind those things that are likely to be positively charged, right? You're talking about your metals. So generally speaking, we're talking about part of the periodic table, the things that will be positively charged metallic, and then we're also including the proton here. And then it is this part of the periodic table where you expect the things to become anionic, to pick up electrons, and to serve as bases. All right, so this just gives us a general perspective of where you identify your acids, where you identify your bases, in the category of the Lewis acid and base concept. But now let's try to be more specific here. In terms of the placement on the periodic table, the hard acids will typically be the alkali metals, and in that list we would include protons. There are some studies that suggest that protons can actually have a metallic property. The alkaline earth metals, and the first row transition metals in high oxidation states. All right, so let's go back to the periodic table to identify those locations. Okay, so here we are, and I'm actually going to clean this up for clarity. So the alkali metals here, we're talking about this entire column. The alkaline earth metals, this entire column. And then when we're talking about the transition metal, so this is the transition metal part of the periodic table. And when we're talking about this part, so we include this part of the table. I'm going to just outline it. And you also include, although they're considered the lanthanides and the actinides, but they're all also part of the transition metals. They're considered late transition metals. When we're referring to the first row, we're literally referring to this row here as the first row of transition metals, and then of high oxidation state. All right, so that's a key thing. High oxidation state. Remember, the charge of the given species is important, the given atom in this case. Now referring to the soft acids. Well, here we're talking about the second row or lower transition metals in low oxidation states. All right, so now let's go back to our periodic table. Let's clean this up so that we can identify the soft metals. So typically we're talking about anything that's here as far as the transition metals that are of a low oxidation state. Okay, so that's a key thing, because that is not to say that you don't have examples of first row transition metals that are of low oxidation states. They do exist. It doesn't imply that you don't have second row or lower row transition metals that have high oxidation states. They do exist. But these are the general features of what constitutes a metal as being hard or soft. And clearly, you're going to have those that are intermediate. So this figure here helps us to generally identify the placement of the elements in terms of hardness, it being intermediate or borderline, and softness. All right, so I would say this periodic table is helpful, but there are a few things that are a little bit misleading. All right, and why I say misleading? Because some of these are labeled as borderline, but they're not exactly borderline. And again, it depends on oxidation state. So here we have the list of the hard acids, the borderline acids, and the soft acids. Now, remember I was telling you that to the right of the periodic table is where you would generally see what would constitute as atoms that are part of the ligands, or the atoms that can't coordinate to metal centers. So now in terms of their properties, here we see those that are the hard bases, borderline, and soft. All right, and this is dictated by the size of the atoms, okay, and then also their charge. Well, when we're talking about the bases now, we're not talking about typically just in an individual atom. As you can see here, these are all molecules. Some of them are charged, right? But what we're focusing on are the coordinating atoms. So for instance, you have the oxygen from water molecule, you have the fluoride, part of the halide series. Okay, so you're focusing on the point of contact with the metal. And here it becomes very interesting because there are examples where nitrogen is a hard base, but you also have examples where nitrogen falls in the category of something that is intermediate. So as we will talk about in a moment, you can actually have a gradient in terms of the description of something being hard, maybe even intermediate, and maybe even soft. So this relative descriptor of hard and softness, well, let's look at an example. So for ligands, resonance can decrease hardness. That's just an example here. But we have this acetate molecule, so we have this carboxylate group that has a resonance. So you resonate the pair of electrons, so these electrons here will resonate through, excuse me, okay, and so now you move the negative charge from one oxygen into the other oxygen. And so if you're focusing on an individual oxygen of the two oxygens, well, that oxygen will have delocalized electron density, which would make that individual oxygen, if you compare it to this ethanolate molecule, so this ethanol molecule, you deprotonate it, okay? Well, that oxygen from your carboxylate versus this oxygen from your ethanolate, well, it would be less hard because of that delocalization. So this has more localized electron density. But then also very interestingly, the carboxylate as a whole group, well, it can serve as a bidentate chelator. And we will talk about this, how denticity of a ligand and the higher density can actually help to increase the stability between the metal ligand contact. So that's another layer here. Something else that to mention is the group that is coordinated near the point of contact, because this group can influence also the relative hardness. So let's imagine that we have a substituent that is electron withdrawing. Well, if it moves electron density away, then that can make something less hard. Or if it can move, so let's move electron withdrawing has its own effect, or even something that is electron donating can make an atom that's coordinating metal center harder, right? So those are components here to think about. Well, you also have the same relative hardness and softness for transition metals. And the relative hardness will be dictated by oxidation states. For instance, iron 3 plus is harder than iron 2 plus. And so you'll commonly find biologically iron existing as either iron 3 plus or iron 2 plus. And so by definition, in terms of hard soft acid base theory, iron 3 plus is considered hard and iron 2 plus is considered intermediate. And that's actually very interesting because they're only different by one electron. The iron 2 has one electron more than the iron 3. If we were to compare the size of the two, now focusing on a particular size, where we have both metals in a 6-coordinate environment, so 6 atoms around the metal center, and we're focusing here on the radius of the metal ion, well, iron 3 plus would be 69 picometers versus iron 2 plus being 75. So then we have that higher charge to size ratio, which dictates iron 3 plus being hard. Another interesting property about iron, just to go on a quick tangent, is that this ability to switch between iron 3 and iron 2, that redox property, is the reason why iron is utilized quite a bit in terms of its ability to facilitate catalysis, to facilitate electron transport. So this ability to fluctuate between hard and intermediate is quite significant in terms of its interaction with biomolecules. Now, we were looking at the hard soft acid base theory to help us understand the principles behind metal ligand interactions, or in general, hard soft acid base interactions. And so there are clear binding preferences. It's been observed that hard acids have a preference for binding hard bases. Intermediate acids prefer binding intermediate bases. Soft acids prefer binding soft bases. These interactions are stronger than those between hard and soft species. So let's use this theory to understand some of the common ways metals bind to biological species. We're going to focus on, in a very simple level, metal complexation by biological species, and we're just look at a few examples. And these are general examples. Let's focus on metal interactions with proteins. Now, for those that are beginning biochemistry, when you're talking about proteins, you can build up this discussion on the amino acids, because the amino acids are the building blocks of proteins. Proteins are essentially polymers made from the monomers, which are the amino acids. So here I'm going to describe a general description of an amino acid. So here is a representation of an amino acid where we have a carbon center. And here, again, I've drawn this for the simplicity of representation. I'm not drawing this structurally correct. We have a carbon center that has an amino group. Okay, this amino group would be positively charged. And then you have a carboxylate group, here it's negatively charged. It also has a proton, and then the defining feature, what distinguishes one amino acid from another, is the substituent on the carbon, referred to as the R group. Now, the points of contact with the metals can come from the following. So I'm going to just clean this really quickly. I've put these stars to identify where you would have a possible coordinating atom to the metal center, where you have a nitrogen from the amino group that can interact with metals. The oxygens from the carboxylate group can interact with metals. And then you can have atoms within the R groups that can interact with the metals. Let's explore this now in terms of a protein, which a protein consists of many amino acids. Okay, so when we're looking at different amino acids, right, there are commonly 20 amino acids. And what I wanted to focus on are the R groups. And the R groups, to help us to distinguish the type of interactions that they will have with metals. All right, so when we're looking at it from that perspective, then what we will see is you will typically have interactions with the nitrogens and oxygens of the R groups. And so here I have these colors to emphasize where you would have coordinating amino acids, or coordinating parts of the R groups of the amino acids. In addition, and let's not forget that the amino nitrogen and carboxylate oxygens can also serve as coordinating atoms. Now, when we're thinking about the R groups, and we're focusing on these particular R groups that are colored in green and yellow, and distinguish them in terms of their hard, soft, acid-base properties. So in this case, they serve as bases, right? Well, then the oxygen would be hard, and then the sulfur of the cysteine, or even of the methionine, would be soft. So you have the OH group from the serine, the OH group from the threonine, right? Again, oxygen would be something that is characteristically a hard atom, and the sulfur, which is more polarizable, would be characteristically a soft base. Oxygen's hard base, sulfur a soft base. Now look at other amino acids. So we're focusing here on tyrosine. I see that this is misspelling, so tyrosine. Okay, so we're focusing on the oxygen from the OH group of that phenyl group. We have these nitrogens from the imidazole group, the amino group from the lysine, the carboxylic acid group of carboxylates from the aspartic acid, and the glutamic acid. Okay, so turns out that the tyrosine, aspartic acid, and glutamic acid, they are hard in terms of their hard-soft descriptor. And then the lysine and the histidine, well, I would say that the amino group from the lysine will probably fall more in the category of hard than intermediate. Remember, nitrogen can really fluctuate here, but the nitrogen from the histidine falls more in line with intermediate. Now, some of the representation of how the amino acids can coordinate. So as we referred to already with the carboxylate groups, well here, carboxylate groups from the amino acids, we can have a monodentate coordination or even a bidentate coordination to the metal center. So you can have different possibilities. Similarly, you see this with histidines, the nitrogens in that group, okay? Well, you can have a resonance of the positive charge from one nitrogen to the other. And as such, then the metal can interact with the nitrogen because you move around the electron density from throughout the actual imidazolium group, right? So you can have electron pairs on the nitrogen, on either nitrogen, and that would facilitate a favorable interaction with the metal center. Here we see the metal interacting with the groups of the nitrogen groups of the lysine, the sulfur of the methionine, the sulfur of the cysteine, the oxygen of the tyrosine phenyl group. All right, so this gives us a general idea of possible coordination. All right, but now thinking about the amino acids together forming the proteins. Well, the amino acids will form peptidic bonds or amide bonds. Right, so here I've shown you in yellow the amide bonds that exist in the sequence of amino acids. Well, basically, that amide bond is how one amino acid conjugates to another. Okay, so you have the carboxyl group from one amino acid that will interact with the amino group from the other. As a consequence of that amide bond formation, you have the release of water molecule. Now, by convention, then, peptides or proteins are a series of amino acids. Okay, so we know that proteins can adopt really interesting structures, complex structures. But when you boil it down to what it is composed of, it is composed of a linear sequence of amino acids. And by convention, we read this linear sequence from the N-terminal end to the C-terminal end. But what does that actually mean? Well, what that means is that first amino acid, we look at its amino group. It has an amino group, right? That's what's free. And then when you look at the subsequent amino acids, you look at the very last amino acid, and you have the carboxyl group that's free for the last amino acid, right? So the N-terminal is referring to the first amino acid, which has that free amino group. And then the last amino acid, which has a free carboxylic acid. Free carboxylate, although the way it's depicted here is not as a carboxylate, it's depicted as a carboxylic acid. All right, so when you hear the terminology N-terminal end, C-terminal end, now you have an appreciation of that. All right, so then you can see where there are potential metal coordinating atoms. Again, the free amino group. Let me actually clean this up so that we can emphasize that. So the free amino group from the first amino acid can serve as a metal coordinating atom. And you'll be surprised, but there are some really significant amino groups from proteins, the amino end, that play a really important role in terms of metal binding transport. For instance, human serum albumin, which is actually our most abundant protein in the soluble part of our blood, it actually has a copper binding site at the N terminus. You can also have metal coordination at the carboxyl end of the protein or peptide. And you can also bind to the amide backbone at the oxygen or even the nitrogen, of any of these. In addition to metal interactions with the R groups of the amino acids. So now looking at the interaction of the metal and the amide backbone. So here's just a representation of how you have moved around electron density so that you have this negatively charged nitrogen, which can favorably interact with the metal. You can also have an interaction with the oxygen of the amide bond. That's not to say that they can't happen. I was just giving you a representation here of the coordination to the nitrogen of that amide bond, but both are possible. Now let's talk about a specific metal protein interaction. So here we're going to just define one example. We're looking at zinc 2 plus binding by the metallothionein, abbreviated MT. So metallothionein is actually a general name for a large family of low molecular weight proteins. These are present at high concentrations. So when we're talking about biological conditions, concentrations of about 2 millimolar are considered high. Okay, so these are present at 2 millimolar in mammalian cells. So just as a point of reference, okay, making a solution of protein that's millimolar is actually quite difficult. It becomes quite gummy, very difficult to pipette. So just imagine that you have 2 millimolar amount of this family of proteins within the cellular environment, and that is one amongst many proteins and other biomolecules within the cellular environment. So you can just imagine how compact it can become. All right, so metallothioneins consist of a single polypeptide chain. So what that means is just one unit. Because some proteins are more than one unit. Also, single polypeptide chain of 61 to 62 amino acids, of which 20 of the amino acids, so 20 residues means 20 amino acids, are cysteine. So we have a very high cysteine content, roughly about 1/3, about 33%. It's very high. All right, so why is that significant? What role does it play in terms of metal binding? Well, the cysteine is actually, as we know, consists of a sulfur group, and the sulfur group are soft, right? So this would be quite favorable for interacting with softer metals. And as such, it's the reason why this protein is utilized, because of its high cysteine content, to store important metals. It actually stores the essential metals zinc and copper. Zinc oxidation state of 2+, copper oxidation state of 1, oxidation state of 2+. I will note that in the intracellular environment, copper is typically copper 1. All right, so here we're looking at how the protein binds zinc. So the protein contains two metal binding regions composed of the 20 cysteine residues. You have the alpha domain, which consists of 11 cysteines that binds 4 zincs. All right, so we see that structure here. It's basically a zinc cluster. Then you have the beta domain, which consists of 9 cysteines, which can bind 3 zincs. So we have this other cluster over here. All right, so let's talk a bit about the coordination here. Well, each of the zincs are located in a tetrahedral geometry, which basically implies a coordination number 4. And now in terms of how the sulfurs of the cysteines are interacting with the zinc, we have those sulfurs that are non-bridging, and there are others that are serving as bridges. Well, what do I mean by serving as bridges? Well, they serve as a point of contact between two different zinc ions. Right. So that gives us an overview of how a metal can bind to a protein, just on a general perspective. Now we're going to switch pages and look at metal interactions with nucleic acids. So nucleic acids are basically the polymers of nucleotides. Nucleotides are the building blocks in this case. So let's focus on an example of a nucleotide and its components. Here we have the phosphate component, the ribose sugar ring, and the base. It is actually the base group that is the distinguishing feature of the nucleic acids. There are other components that can differ from nucleotides, for instance, the number of phosphates, and even whether or not you have a oxidized or reduced ribose ring. But this is just um, the simple perspective of what constitutes a nucleotide: the phosphate, the ribose sugar ring, and the base. All right, so here I'm showing you the common nucleotides that constitutes the nucleic acids. And so here is a descriptor of where you would find these nucleotides, whether you're talking about DNA, RNA. Now let's talk a bit about the composition of a DNA strand. Now, what connects one nucleotide to another is the formation of what is called a phosphodiester bond. Okay, you have the phosphate group of the carbon 5 of one nucleotide that will bind to, or the carbon 3 prime of the other nucleotide. And so that's how you get your phosphodiester group. And that forms your phosphodiester backbone. So you see this strand here, and you see your phosphodiester backbone. All right, so in terms of how we read by convention the nucleotides, well, we read it from the 5 prime to the 3 prime end. So what does that mean? Well, the first nucleotide, we have a free phosphate, and that is at the 5 prime carbon of that nucleotide. And then your very last nucleotide. So here we're just looking at a strand, okay, that consists of 3 nucleotides. Well, the 3 prime end has a free hydroxyl group. Whenever there's a point of contact, right, what you will see are these phosphodiester bonds between the 2 nucleotides. So the phosphate group at the 5 prime end, the nucleotides linked by phosphodiester bond formation. The bases engage in hydrogen bonding that results in characteristic base pairing. And so here, I'm going to just clean this up a bit just to emphasize that. We're using this symbol to represent where there are possible points of hydrogen bond contacts. And so the typical base pairings between A and T, okay, the adenine and thymine, and G and C. So that would be the guanine and cytosine. Okay, so here we have the representation of the hydrogen bonds that can occur between these, the base pairing that can occur between these nucleotides. So between A and T, we have 2 hydrogen bonds. And then between C and G, we have 3 hydrogen bonds that are possible. Okay? And then structurally, we can see how it can form the helices of the DNA. We'll see that in a moment. Okay, so here we have a representation of a structure of the beta DNA. I will note that DNA can become much more complex, compact, okay? But this is just a representation of how you have the base pairing and how they stack up on one another. So this is the hydrogen bond interaction between the bases. You have the base pair stacking. You get the arrangement of the nucleotides so that you have this helices where you have one component that is defined as a major groove, the other component defined a minor groove. All right, so this just gives us an overview structurally of how the nucleotides interact, and you get this double-stranded structure. Okay, there's 2 strands interacting with one another. And what's drawing that interaction between the strands are the base pairing, the hydrogen bonds between them. All right, now from the perspective of metal interactions, now here we will generally define where there can be coordinating atoms. So you can have coordination to the phosphate group, coordination to the backbone, the phosphodiester backbone, coordination to either the nitrogens or even the oxygens of the bases. Okay, so I haven't pointed to all of the spots, but generally speaking, you appreciate that we're talking about the oxygens or the nitrogen atoms within the actual DNA, and that being a point of direct contact between an atom from the nucleic acid and the metal. But now, in terms of more specific, and so even here, I'm just using general cartoon representation. Specific types of interactions can come in of the following form, where the metals can cause intrastrand or interstrand crosslinks. All right, so what does that mean? All right, so here we have this cartoon representation of the double-stranded nucleic acid. So this is one strand here, the other strand, okay? So when we have an intrastrand, that means that within the same strand, you can have a metal that's connecting two nucleotides along the strand, okay? Now let's clean that up. Or you can have interstrand. That means that you have a metal that can bind to two nucleotides, but these nucleotides come from two different strands. Okay. Something else that can happen is that you have a metal, but in the form of a metal complex, a metal compound, that can intercalate into the base layers. All right, so what does that actually mean? Well, here we have a representation of a drug. Let's imagine that drug is a metal compound, and it's intercalating, so it's nudging itself right in between the base layers, right? So what are the properties of that particular compound to enable that interaction? Well, as you can see, the representation here is that you have these base layers. You basically have these aromatic layers, and they're, to an extent, they're planar, right? So the typical drug, or even if we're referring to a metal compound, will have to have a certain planarity in order to allow it to fit within the layers, okay? So planarity, aromaticity are favorable things for this type of interaction. So it means that not any metal compound will be able to facilitate this interaction. You also have metals interactions that can be of the nature where a metal serves as a bridge between the nucleic acid and another biomolecule. So here, just the representation of a cross-link between nucleic acid and protein. All right, so in terms of why people explore these type of interactions, well, for therapeutic purposes, let's say you want to design something that is an anti-cancer agent, and you might want to design something that can directly interact with the DNA of cancer cells. So you want to disrupt the structure of the DNA, such as to prevent the DNA from replicating. Right? So these are things that people think about as far as the kind of context that can be facilitated. For other purposes, maybe people want to label nucleic acids, so they may use metals for this purpose. Right? So it can play the role of, or it can be for purposes that are therapeutic based, for imaging, or so forth, right? So there are different reasons why people want to understand or have explored how metals can interact with nucleic acids. All right, so that concludes our beginning discussions about fundamental bioinorganic chemistry. But in our subsequent lectures, we're going to dive more deeply into the thermodynamics behind their interactions and even some of the related kinetics of the ligand exchange. Okay, I'll see you next time.